I'm on slide 0, and I'm already a little bit off script because a lot of the motivation and background, which is covered in the last presentation, in terms of using DFT or TBDFT, more specifically to predict fragmentation and first generation radicals of these PFAS molecules that we're looking to replace for environmental reasons. And I'm sure everyone here already knows the motivation behind this, but my first part of my PhD was incredibly theoretical, so I'm including this just to say that I finally have an answer when somebody asks me why what I'm doing actually matters. And this is taken from a press conference, a press statement from the White House last month, where they talked about how they're going to continue working to identify new strategies and new research in order to find these good, useful replacements for these harmful PFAS molecules. And so the project started with us using the R matrix code from Quantemol. Okay, so let's start with our ideal workflow. So if our project works, what is our aim? We would love to be able to talk to partners like Quantemol, where they have an idea of, or industry partners where they have an idea of what fragments they would like at the end, what cracking would be ideal, and we can use our sort of self-built database of all these molecules that we're running to find out what features of the molecule suggest which radicals are at the end, and then we make a short list of saying, okay, we run the first generation radicals on these molecules, they break here and here and here initially. Hopefully you can sort of shortlist or shortlist. And so we started by using the R matrix code to calculate the electronic excitation states cross sections for two molecules, one with a double bond. And here yes. Here it's very clear that there is lowest line triplet state. So we can run our dynamics entirely on this lowest line triplet state, which is very nice because it's so much cheaper than our effect down. If we look here, I'm sure I'm convincing nobody that there is one lowest line triplet state here. But if we run non-adiabatic dynamics on both of these triplet states, these two lowest line ones here, we find out that the highest triplet state relaxes into the first triplet state within about 50 seconds. And so we say, okay, let's assume this happens instead of 50 seconds instantly, and then we go back again to running everything on the lowest line, and everything remains cheap and it remains nice. And so initially, our group has developed methods for running singlet states, so photo excitation, this sort of thing. And it's led to a method called ab initio multiple cloning, which we use for multiple different photo dissociation simulations. And the idea is that essentially moving singlet state to triplet state shouldn't really be that big an issue at all. And so in order to do this, in order to make it entirely on the fly, we're using the spin flip time dependent DFT, or if you're brave enough to do the punk with the SF PPVE, which we're using the QCAM package in order to do, which means that we can sort of shape a time step, calculate the forces, we can have a time step, etc., so on and so forth. And so ab-initio multiple cloning is a trajectory-based method for solving the Schrodinger equation, and with the all trajectory-based methods, the sort of key question is, okay, how are you going to actually guide the trajectory? And our answer has always been error trajectories because they're fully quantum, but they're also cheap. So you have this sort of best of both worlds that deal to it. You're taking the average of the potential energy, so by population. And in order to counteract what would be a disadvantage when you leave this sort of crossing region, and perhaps the wave function is bifurcating or potential energy surfaces that sort of divergent from each other, you have this cloning procedure, where we can essentially create another few basis functions within the trajectory itself, such as our trajectory itself can bifurcate, just like the wave function works. But I suppose it's also worth reminding that here, for these sort of initial linear calculations, everything is on one triplet state. So this is very useful for when the going gets tough. But right now, we seem to be okay just using one initial state. And so Quantemol, they provided us papers, some experimental papers where they're looking at replacement molecules for C4H3F7O, where all of these molecules have a GWP that's at least half of the molecule that's normally used, which is a great start. And so essentially we ran 500 trajectories of each molecule at 5,000 Kelvin, 500 femtoseconds, and we can essentially look through the coordinates that are generated, find where the bond breaks, find which bond breaks, and therefore we can hopefully paint a full picture of initial fragmentation. And so if we start with the alcohol, we see that the H in the oxygen is very quickly ejected in roughly half of the cases. So all of these graphs are average of 100 trajectories, just because I think everybody likes to think things out of 100. And so we can see that in roughly half of the cases, H is ejected very, very quickly. And then we have some carbon-carbon breaking. We have some CH breaking here. But interestingly, the CO almost never breaks. And in fact, it never breaks after 100 femtoseconds. And this is due to this very quick ejection of the hydrogen, due to the oxygen is not willing to essentially break another bond into the molecular oxygen radical. And the CF bonds, they're relatively stable, they're sort of the strongest single bond that you can imagine for carbon, and so they barely break. But instead, if you look at something that's not an oxygen, where this H isn't being very quickly ejected, you have a very different picture. So here, we have the CHs being the very quick ejection, but the CO bond now is actually ends up being the most broken. And we're assuming this is due to some sort of initial localization of the triplet state. So we're hoping that if we do a full diagram data, we're going to see that the initial spin density is very concentrated around this oxygen, and will sort of disperse and break bonds as time goes on. The CC bonds increase, and we assume that this is due to the oxygen acting upon CC bonds. And so this is an asymmetrical isomer. And if we move to a symmetrical one, where the oxygen is in the middle, we see a very similar picture in terms of bond breaking. But luckily everything is shifted over to the left and slightly up, which means more bonds are broken, which further supports this theory that oxygen is playing a critical role, because now the oxygen here is affecting both this carbon bond and this carbon bond, leading to a lot of breaking quicker and also more breaking overall. The CF bonds are also increasing because now we have more fluorines in proximity to this oxygen. And for the sort of painting this picture, that oxygen is very important. But if we also look at oxygen and the molecule, if we compare the symmetrical and the asymmetrical isomers, we find that these bonds are actually weakened, because if you look at a trajectory where one of these carbon bonds breaks, so either the 1 to 2 or 2 to 3, we find that the second carbon-carbon bond breaks roughly 45%. But in the asymmetrical isomer, only 7.4, 7.5% is the second CC bond. So it's showing that both CC bonds that are next to the oxygen, they do break, and they break even after the molecule has already begun fragmenting. So it introduced another sort of aspect, another function to the molecule, that is this double bond. We see yet again another slight change in behavior, which is that the double bond is actually the first to break and also the most common break. And then we have our sort of what's becoming a standard pattern of CO, CC, and then the strong CF bonds at the end. And because we have sort of the coordinate throughout everything, we can look at, so this is a general picture of bond type, but we can look at each individual carbons to see which carbon experiences the most bond breaking. And if we do this, we find that the carbon experiences the most. It says carbon is attached to both the double bond and the oxygen. Then there's a large jump downwards, where the next highest ones are the fifth carbon that experiences the double bond, and the third carbon next to the oxygen. And then there's another jump down, where you essentially find that the carbons that aren't next to a functional group, they sort of decrease in bond breaking, so further away from a functional group that we're interested in. And even here, where the fluorines are very sort of, they don't look particularly interesting, it's practically linear. But if we look at each individual fluorine environment, we find that there is actually something going on. So this CF bond here on the carbon experiences both the oxygen and the double bond. This one breaks incredibly quickly, and also 4 times as much as the next highest one, which are the fluorines on the double bond, which has this sort of sharp rejection that we're looking to see, because it goes to a double bond, which we're hypothesizing is localized in the triplet state, and then it sort of flattens off as if this fluorine itself is dominant. And so if we turn from looking at the number of bonds broken into overall fragments left, there are a lot of PF2, a lot of CO, and this would essentially be our model's allegory to a mass spec. And so when we look at the experimental paper from which we took these molecules, we're essentially agreeing with this strong CO signal that we observed, and we're also agreeing that low mass fluorocarbons are predominant, which is good. And so if we compare fragments between the molecules, we find more agreement with the experimental paper, and such that PPVE, which is the larger molecule with a double bond, has a larger number of fluorocarbons, which is essentially just without the oxygen, than the two isomers, the amethyl and the methyl one. And we also find that there are a higher number of large mass fluorocarbons in the asymmetrical than the symmetrical, which we can expect because the oxygen acting on both CC bonds is essentially fracturing the molecule more. We need the smaller radicals, smaller fragments at the end. And therefore, we're sort of using these molecules to begin to build up a picture of our sort of rules of the fragmentation for the first radicals, initial cracking, whatever you'd like to call it, which is that the position of an oxygen is very important because you can use it to control the size of the radicals created. The functional group, however, is also important, as an alcohol very rarely breaks. The CO bond alcohol very rarely breaks, sorry. So I'm not exactly an expert in at all to do with etching, but if there was ever a reason that we wanted a carbon TFO radical, this would be the way to go. Hydrogens, they have a fairly consistent behavior in terms of you can sort of move them around the molecule, but they're always going to be ejected quickly and then die off. Double carbon bonds associate more rapidly with single carbon bonds, which sort of you would expect double carbon bonds to be stronger, but in these circumstances, they're not quite. And we also know that the sort of localization effect of a double bond and the proximity to oxygen, they are cumulative. So a double bond encourages bond breaking, and an oxygen atom encourages bond breaking, and both really encourage bond breaking. And so in conclusion, we sort of have our ideas to go further. We're looking at different electronic structures, theories in terms of, do we need spin flip if we're just staying on the lowest line triplet state, if there's no coupling? Do we need this sort of more expensive, more rigorous version, or is non-spin flip sufficient? We also are looking at temperature dependence. So 5,000 Kelvin is obviously a lot higher than wherever experiment will be sitting, but 5,000 Kelvin allows us to sort of run our trajectories within a reasonable time. And the hope is that if we bring down the temperature, we can see some sort of way to extrapolate down to these experimental temperatures. More molecules. So I think for our project, almost our entire molecule pipeline has come from Quantemol, supplying us with relevant molecules. And I'm sure that people here have a lot of ideas of things that would be interesting. Like you could even look at F6 and then branch out into those things. So yeah, thank you for listening.